Morning, everybody. Let's take a look at the solutions to the problems I posted yesterday from the Passwater 2020 AB free response questions. Again, I would anticipate questions that look pretty similar to these. So let's go through. And feel free to practice these a little bit if you know you need to, okay? So we have a table of values here. We have x values and we have f prime of x values in the table. On the interval -2 to 10, the function f is twice differentiable with f double prime of x greater than 0. Selected values of f prime are given in the table above. It is known that f of 7 equals 4. Okay, so we're working on the closed interval -2, 2. They tell us f is twice differentiable, so automatically f and f prime are both continuous. And think about what this means. If f double prime of x is always positive, right? If a derivative is positive, the function it came from, in this case f prime, is always doing what? Increasing. And you can look at the table of values and you notice from left to right, these values are increasing. With this piece of information, we know that f prime is strictly increasing. Okay. Selected values of f prime are given in the table above, and then they give us 1 point on the original f function, f of 7 equals 4. Okay. Part A, approximate f double prime of -1. Is there a time c on the interval -2 to 7 at which f prime of c equals this approximation? Okay, let's worry about f double prime of -1 first. Okay. So for f double prime of -1, okay, we know that f double prime is the derivative or slope of f prime. So like we see in a lot of these table problems, we're just asked to approximate the slope of the function in the table at -1. Okay, so what's going to be the best interval to use to approximate the slope? Well, -1 is right between -2 and 0. So we're going to use this first interval. All right, so we're going to approximate the slope of f prime on this interval. Okay. So f double prime of -1 will be approximated by, I'm going to write it like this, f prime of 0 minus f prime of -2 over 0 minus -2. Change in y over change in x. Grabbing the values from the table, f prime of 0 is -2 minus -8 over 2 gives us 6 over 2, which is 3. Okay, so the approximate value is 3. Now, is there a time c on the closed interval -2 to 7 at which f prime of c equals this approximation? Now, usually when they ask us about derivatives equaling certain values, we're looking at the mean value theorem. But this one's actually not the mean value theorem. Okay, f prime is the table of values we're looking at. So we want to know, is there a place where f prime itself has to equal this approximation of 3? Okay. Is there a place where f prime of c will equal 3? That's the question. Okay. Well, look, we know that f is twice differentiable. So f prime is continuous. Okay. And if you look at the values in the table, notice that f prime is strictly increasing. At one point, we have a y value of 2, and then we go to a y value of 6. If f prime is continuous, to get from 2 to 6, we would have to cross over 3 to get there, right? To go from one y value of 2 to the y value of 6, we've got to cross over the y value of 3 to get there if the function is continuous. So this is actually not a mean value theorem, but rather intermediate value theorem problem. Okay, since f prime is continuous, by the intermediate value theorem, there is a c on the interval. It's really on the interval from 2 to 3, but we're just going to state it on the interval given. There's a c on the interval given such that f prime of that number would indeed equal 3. Okay, so that was application of the intermediate value theorem. All right, so give that a little thought. Hopefully the first part not too bad, and shoot me some questions if you have them. All right, I'm going to clean this up, and then we're going to take a look at part B. Okay, evaluate the integral from 0 to 3 of 5x times f double prime of x squared minus 2 dx. Show the work that leads to your answer. So I'm going to bring this down here where there's a little bit more room. Okay, make sure I got that right. Okay, so the hint was use substitution. Now, why are we using use substitution? Well, we're integrating and we do have a product, 5x times f double prime. We do have a quantity inside of the f double prime function. Okay, there's our u. So let's see what happens if u is x squared minus 1, du becomes 2x dx. Looking at the interval, I have 5x dx. Look, I'm just going to do this. I'm going to match up the x dx. To replace x dx, I would need a 1/2 du. The coefficient of 5 is just going to stay there. It's no big deal. I am going to do my change of bounds as well. Let's look at see what u equals when x is 3. 3 squared minus 1 is 8. When x is 0, 0 squared minus 1 is negative 1. So we now have bounds that go from negative 1 to, oh, excuse me, not 8, 7. 9 minus, did I do this right here? Where's my mistake? Something's off. Son of a gun, it's x squared minus 2 in the quantity. Let me change that real quick. Thanks, folks. Sorry about that. Okay. That will have a slight effect. Okay, sorry about that. X squared minus 2 is our u. Okay. Doesn't affect the du. Still the same du, 2x dx. 3 squared is 9 minus 2 is 7. 0 squared minus 2 is negative 2. There we go. All right, so put it all together. New integral is going to go from negative 2 to 7. Now, here is going to be f double prime of u. The x dx became 1/2 du. The only thing that's left is that 5. I'm going to put that out front with the 1/2. Okay, and there we go. Chip away at this thing, put it together. Okay, so out front we have 5/2. I'm going to write it like that. Integral negative 2 to 7 f double prime of u du. Keep your coefficient. When you integrate f double prime, what is that going to take you back to? F prime, which we will evaluate from negative 2 to 7. So we're looking at 5/2 f prime of 7 minus 5/2 f prime of negative 2. And now let's grab the values from the table. All right, we have a table of f prime values. F prime of 7 is 11. And f prime of negative 2 is negative 8. And so we're looking at 55/2 plus 40/2 for a grand total of 95/2. Okay. All right. Let's take a look at part C. The function g is defined by the equation g of x equals f prime of 2x cubed minus 9x squared. Find any critical values of g of x and classify as local min, max, or neither. So critical points are where the first derivative is 0 or undefined. And then we'll test the sign change around those points to determine if we have max or mins. Okay. So again, the hint here was to use the chain rule to take the derivative of this thing. We have a function inside of another function. Okay. So g prime, the derivative of f prime would just be f double prime of this thing times the derivative of the inner quantity. So that's going to end up being 6x squared minus 18x. So there's the derivative of g. Now we're going to want to set that equal to 0. Okay, and so we have a product. We're looking at where either f double prime of this equals 0 or where this quadratic portion equals 0. In terms of f double prime, let's remember we were told that f double prime is always positive. Okay, so this is not going to equal 0. So we're really now just focused on where the quadratic portion equals 0. So let's see, we can factor that. We're going to have zeros at 0 and 3. And what are we on? The closed interval -2, 7. Okay, so we found the critical points of G. X equals 0 and 3. Okay, now again, let's test the sign. F double prime is always positive, so that's great. And so we're really just looking at the sign of this in these different regions. If I take a number like -1, which is between -2 and 0, we get a negative times a negative. So we're positive, and so G would be increasing. If I take a number like 1, that's a positive times a negative, decreasing, and a number like 4, positive times positive. So it looks like at x equals 0, G has a relative max because G prime changes positive to negative. At x equals 3, G has a relative min because G prime changes negative to positive. And remember, on the AP exam, let's write full sentences, okay, and make it nice and neat. All right, but relatively straightforward stuff there. Practice it a couple times if you know you need to. I know you can do that stuff. Okay, part D. Again, let me clean up a little bit here. Rewind and pause as you need to. Part D, use a left Riemann sum with the 4 subintervals indicated by the table to estimate f of 0. Is this an over or under estimate of f of 0? Okay. It's Riemann sum, so we know that we're going to be finding the area under the graph. Okay, left Riemann sum with 4 subintervals indicated by the table. Okay, so we're doing a Riemann sum of f prime. Now, if you think about it, there's really 1, 2, 3, 4, 5 subintervals. Okay, they say use the 4 subintervals indicated to estimate f of 0. Okay, look, we're going to set up a bounded integral to do a Riemann sum. Let's figure out what the bounds are going to be. 0 is certainly going to be one of the bounds. Okay, if I am going to integrate f prime to get back to f, and I want f of 0, certainly 0 is going to be a bound. The other bound is going to be any x value where we know the y value of f. And that's going to be at 7. So they said the 4 subintervals, because we're really just working on the interval from 0 to 7 here to set up our Riemann sum. Okay, so we're going to set up the bounded integral from 0 to 7 of f prime. And let's see what that looks like. Okay, so we're going to have the integral from 0 to 7 of f prime. And this is one of those fundamental theorem of calc setups. We're going to do the Riemann sum approximation for the integral on the left, but on the right-hand side of this equation, we're going to write f of 7 minus f of 0. Right? Fundamental theorem of calc, bounded integral equals antiderivative of top minus bottom. Okay, so I'm going to do a scatter plot off on the side for the Riemann sum. The interval 0, 7. We have 0, 2, 3, 4, and 7 for x values. And let's see, 0, -2, 2, 2, 3, 6, 4, 8, 7, 11. Okay, so a quick scatter plot, and now we're doing a left sum. So the heights come from the left side. So actually the first one's below the axis. If I go down, I get a rectangle down there. On 2, 3, I get this rectangle. On 3, 4, and on 4, 7. Okay, so that's what our areas are going to be made up of, these 4 rectangles. And so let's say for the first rectangle we have a base of 2 and a height of -2. Second rectangle, 2 to 3 is a base of 1 and a height of 2. 3 to 4, base of 1, height of 6. 4 to 7 is a base of 3 and a height of 8. There's our Riemann approximation. This is going to be f of 7 minus f of 0. What do we know about f of 7? That's 4. So I'm going to go ahead and sub that in. And now we can figure out what f of 0 is. So we get, let's see, negative 4 plus 2 plus 6 plus 24. Negative 2 and 6 is 4. And 24 is 28. 24 equals negative f of 0. So it looks like negative 24 is going to be the f of 0 value here. Okay. Let's see, is this an over or under estimate of f of 0? All right, well, let's take a look. Okay, remember, f prime is increasing. So it looks like the areas of these rectangles is going to be an under approximation. Okay, here's where we need to be careful. This 28 is an under approximation to the actual value. Okay, so the actual area is going to be some number bigger than that. And so, let's see, subtracting 4, we get to 24. So this is actually going to be bigger than negative f of 0. Okay, when we multiply both sides by negative, this is going to therefore be smaller than f of 0. Okay, so a little bit tricky on that end of the justification, but I think it's easy to see that the area of the rectangle is under approximates. Okay, and therefore, like I said, the 28 was a under approximation to the actual value. So the 24 is an under approximation to the negative of f of 0, and then multiplying both sides by negative 1 kind of changes things around. That negative 24 would therefore be an over approximation. Okay, a little tricky, but put some thought into it, and hopefully you get it. Shoot me an email if you need to. And last up, part E, with the slope fields and the tangent line approximation. Okay, let me clean up a little bit here. A little more room to work. All right. Let y equal h of x be the particular solution to the differential equation dy dx equals y times f prime of x over 2 times the quantity x minus 1, with the initial condition h of 2 equals negative 1. On the axes provided, sketch a slope field for the differential equation at the 9 indicated points. Then use the line tangent to h at x equals 2 to approximate h of 2.1. Okay, so we got to figure out what the slope of h is at each of these points. And here's the derivative of h. Okay, h has this as its differential equation. Okay, so I'm going to write down these points. We've got 0, 1, 0, 0, Okay, so we got to figure out the slope at each of these points. Okay, so we're gonna sub in for x and y here. So like 0, 1. Okay, subbing into dy dx. 1 for y, 0 for x. And now we got to look at the table to see what f prime of 0 is. F prime of 0 is negative 2. So we have 1 times negative 2 up top over 2 times negative 1 below. That ends up being a slope of 1. It's 0, 1. So come up and just draw a little dash of a slope of 1. Okay, so we got to take our time, go through each of these. Okay, so for 0, 0, we're going to have, well, as soon as I plug 0 into the numerator, the whole thing is 0. And as long as the bottom's not undefined. So that's just 0. In fact, anytime y is 0, it looks like that whole thing's going to be 0. So that's nice. I'll do that. Okay, so I'll get those quickly. I just noticed that when y is 0, that whole thing is 0. Okay, 0, negative 1. Let's see. So negative 1 times f prime of 0, 2 times 0 minus 1. F prime of 0, again, was negative 2, so we get positive 2 over negative 2 is negative 1. Okay. All right. Moving on. 2, 1. Okay, we're going to have 1 for y, f prime of 2 for x, 2 times 2 minus 1 down below. F prime of 2 is 2. So we get 2 up top, 4 below is a half. Okay, so we're going to have a slope of a half. Doesn't need to be perfect, but it should be less steep than a slope of 1. Okay, now let's look at 2, negative 1. So we're going to have negative 1 times f prime of 2 over 2 times 2 minus 1. So we're going to have 4 in our denominator again, and we'll have the negative of f prime of 2, negative 2 up top. So negative a half this time. Okay. And now a couple more coordinates to go. Let's take a look at 3, 1. Okay, 1 for y times f prime of 3 over 2 times 3 minus 1. Oh, let me see. So here we get 1 times f prime of 3 is 6 over 2 times 2 is 4, so 3 over 2. Slope of 3 over 2 there. A little steeper than a slope of 1. Boy, I'm all over the place. Sorry, guys. That should be down there, that point I drew. Okay, 3 over 2, right about like that. Maybe a little steeper. And then negative 3, 1, or 3, negative 1, excuse me. That's just going to be negative f prime of 3 over 2 times 3 minus 1 is negative 6 over 4 is negative 3 halves. Okay? So there we have that. I'm going to double check the 2, 1 and the 2, negative 1. I think maybe I made a careless mistake real quick here. Let's see. If I go back to 2, 1, that's going to be 1 f prime of 2 over 2 times 2 minus 1. That should be a 2 in the denominator. 2 times 1 is 2 in the denominator, excuse me. And in the numerator, f prime of 2 is 2. So we actually do just get back 1 here. I'm sorry. And this one's going to be negative 1. So you guys may have been on top of that. Okay, so in any event, I butchered it a little bit, but just try to go slow and be careful. I realized I made a mistake, so I went back and fixed it, okay? So in any event, we've got these slopes, all right? And there's your slope field. So again, just take your time, be careful with that. Now, in terms of the line tangent to h, okay, use the line tangent to h at x equals 2 to approximate h of 2.1. Okay, so y minus y1 equals slope times x minus x1, which is 2 here. y1 is going to be whatever h equals it to. Well, they told us that's negative 1. So y minus negative 1 equals slope times x minus 2. Slope is going to be h prime of the point 2, negative 1. Okay, so if we look at our slopes, I already computed the slope for 2, negative 1. That's negative 1. So the equation becomes y plus 1 equals negative of x minus 2. Or if you want, y plus 1 equals negative x plus 2, or y equals negative x plus 1. And so now to approximate h of 2.1, all we do is plug in 2.1 into our tangent line. Okay, we should get back negative 1.1. Okay, again, some of these are tricky, some of them not as bad as others, but worth looking at this a couple times, trying a few times, see even if you can get through the work, because again, your exam's going to probably be pretty similar to these types of questions. Okay, folks, hope everybody has a good day, and talk soon.